All right, now actually let's apply the inclined plane situation to problem one and problem two. So here's the idea. Ooh, don't like that. So we have the inclined plane like this at an angle theta. We have our box M, and let's just draw the free body diagram. Again, we have FG pointing down. The reaction force goes perpendicular to the inclined plane like that. And then our components. So to draw FG cos theta, I would start along the line of R. Don't draw over it. Trace it with your finger trace it with your pencil without actually putting the pencil on the arrow. And then once you get past the line, draw a dotted that should go in the same direction. And that's FG cos theta. And then absolutely at a 90-degree angle to R, FG sine theta goes this way. Now, in the y direction, this is not a fraction, this is just me underlining the letter y to create a column, and same with x. So I'm going to say that R balances FG cosine theta because the forces bounce in that direction, the box doesn't accelerate, the arrow crash into the inclined plane. So we get that R is FG cos theta. True, but not useful for this part, but we will use this when we get to friction. Because in question number 2, we need to remember that the friction is mu times the reaction force. Just as an aside. In the x direction, we only have Fg sine theta, and the effect of that is that the mass accelerates. So I did the work up here for number 1, I'm going to apply it here. So we want the reaction force and the acceleration of the box. So R is Fg sine theta. I want to be clear. On the IB exam, the IB needs to see all of this. Okay? So R is Fg sine theta. I'm going to put in my numbers. That's going to be 2 times 10. Fg is m times g times the sine of 40. And when we actually solve for the reaction force, we will end up getting, let's see, 12.86 newtons. Now let's get the acceleration. Fg sine theta is ma. That's mg sine theta equals m times a. People notice that the m's cancel. Good. So we got 10 times the sine of 40 equals acceleration. And the acceleration works out to 6.4 meters per second squared. And I guess if we wanted to use sig figs here, I suppose I would write this a little bit better as 12.9 newtons. That would be the better way to write it. All right, now for number 2. If the object slides down the inclined plane at a constant velocity, we want to show the coefficient of friction is given by mu equals tan theta. So this weird letter mu, that's the coefficient of friction. Constant velocity means the acceleration is 0. That means forces balance. Now, mu. I didn't give it a subscript, but let's just kind of be clear. We have mu kinetic or dynamic, which means it's the friction acting on an object that's moving. We have mu static, which is the friction acting on an object at rest. Sometimes I'll just call it mu, just to denote that there's a friction. So this would be a moving friction. And the only reason we care about this is we need to note there's a formula in the data booklet. It says the friction force is mu times the reaction force. So we slide down an inclined plane at constant velocity. And so let's redo all the physics. So we have a gravity force. Redraw this. We have the reaction force. We have Fg cos theta. Notice it's in the same line as R. Fg sine theta. And then we have our friction force like this acting in the opposite direction. Now we're going to set up equations, and this is again our axes. So this is the y-axis, and this is the x-axis. So I have one arrow pointing to the right here, one arrow pointing to the left there. Well, yeah. So in the x direction, I have FG sine theta minus friction, and they balance. I want to be really clear. This is what the IB tests on. You have to be able to reproduce this diagram. And if they change the picture, you need to be able to add in the extra forces and be able to creatively come up with that on your own. And then you have to recognize how to translate this picture into a new original, not given to you in the data booklet equation. And then we're going to have mg times the sine of theta. And the way I do it is by reading the picture. I have this arrow here, I have that arrow there, I subtract them and they balance. So mg sine theta minus friction equals 0. So remember, our goal is to actually come up with a formula for mu. Don't let the phrasing of the question confuse you. We will always have the same approach to each problem, which is number 1, free body diagram. Number 2, set up balanced and unbalanced forces. Then I'll read the question, and then I'll use the thing I did in step 2 to solve. These bounce and unbalanced equations are what I use to solve. So here, in the y direction, I end up getting r minus fg cos theta equals 0. R equals fg cos theta. Now, where does the friction part come in? Right here. This is r. This is the f. And I can do a little substitution here as mg times the sine of theta minus mu times the reaction force is 0. And now I substitute. This goes into here. And when I finally simplify, I get mg sine theta minus mu mg cos theta equals 0. I can divide out the mg's. I'm going to end up getting sine theta equals mu cos theta. I divide both sides by cos theta. And I get that mu equals the tangent of theta. That's question 1 and 2. I'm going to take a look at question 3 and 4 and possibly 5 in the next video.